good morning grade 11s. This video is basically on how to answer questions, exam questions about Euclidean geometry. So what I've done is I've made a bit of a summary page for you guys, and I said that this would always be a good idea to use during the exam. So if I was you, I'd come up with like maybe a simplified version of this, even smaller and shorter, just so you can write the keywords, before you start your paper, write it down so that once you're answering the questions, you have all the theorems in your head already, and you can refer to them through the exam. Okay, I might split this over into 2 videos, depending how long it takes to answer all of those questions. Okay, so basically the summary is just to remind you, I've actually left one theorem out because I didn't feel like it's not very relevant to a lot of the questions. But okay, so the first one, I don't know if you recall, but it's line drawn from center perpendicular to chord. So essentially, remember, if you start at the center and you draw a perpendicular line to a chord, it bisects the chord. And also this orange one is, the inverse kind of the theorem. So if you draw it from the center and you draw it to the midpoint, then you know it's perpendicular. So the first reason that you can use is line drawn from center perpendicular, then that basically tells us that this line is bisected. Or you can draw it from the center to the midpoint, so you know it's bisected, and then you can say, okay, because it's bisected, I know that that is perpendicular. So you can use either of those. The second one, angle at center equals 2 angle at the circumference. That was this one. So in other words, this purple one is double the size of that one at the circumference. And remember, there were some odd looking ones as well. This is just, as I say, it's a summary. So you can write down your summary however you choose. The third one, I call it Bowties. That's that one where it looks like a little bow tie. And your reason that you use is angles in same segment. And essentially those two will be equal and these two will be equal. And remember, what's important about this one is that those points must lie on the circumference. Can't be anywhere else. Okay, it can't just be a random bow tie. All right, number 4, opposite angles in a cyclic quad. I don't know if you remember, a cyclic quad, either they'll tell you it's a cyclic quad, or if all 4 of the corners are on the circumference, then you can assume it's a cyclic quad. And in a cyclic quad, remember, the opposite angles are supplementary, which means that it adds up to 180 degrees. I also just wanted to show you, remember, this was how you prove that a quadrilateral is cyclic. There's 3 different ways. Either you prove that the opposite angles are supplementary, or you prove that an exterior angle equals the interior opposite, or you use that same segment thing, so the bow tie thing, and you show that those 2 are equal. Okay, that was from a previous video. So when it comes to the cyclic quad stuff, they might ask you to prove that. Actually, sorry, sort of going back to this bow ties one, I also wanted to remind you that there was different plays on this bow tie one as well. So this bow tie one was essentially saying from these 2 points, if I do that, and then if I go from these 2 points to there, those 2 angles are equal. But remember, there was a play on that if this line, okay, subtends that angle, which is over there, and then I have the same size line over there that subtends this one, those 2 will be equal. Okay, so if it's in 2 separate circles, or if it's in the same circle, if it's the same length here, okay, it will subtend the same angle. All right, and this will actually crop up in one of the examples that we do now. Okay, then tangents from same point, that was if it starts at the exact same point and it's a tangent to each sides of the circle, those 2 lines are equal. Remember, it looks like a hat. Okay, and then last one, this was that really difficult one, angle between line and chord, or I'm actually going to put your or, what I like to say is tan chord theorem. So you might see me use that as a reason out of habit because that's what I was taught in school. But remember, that's the one where you count 1, 2, 3, 4. 1, 2, 3, 4. And then 1 and 3 will be the same. If I go this way, 1, 2, 3, 4. The 2 purples are equal to each other. And then lastly, I forgot to put this in there, but it's not quite a theorem. It's just something we use. If you have a radius and a tangent, remember they will always be perpendicular. And we say tan perpendicular to chord. Radius what did I just say? Sorry. Radius perpendicular to tangent. I had this in my head. Radius perpendicular to tangent, because this is a radius and this is a tangent, but it will always be that the radius and the radius is perpendicular to the tangent if they touch. And then also don't forget, if you have more than one radius, they are equal, and if you want to say that something is equal because it is a radius, then you just write radii in the background. Okay, so these two were not theorems, but yeah, you must just use them and know them. Okay, so what I've done for the examples, they were really small when I printed them, so I went and reprinted the picture quite big so that you guys can see it on the video. But what I'll do is I'll just read out the information so that you guys can hear, and I'll draw it on. Okay, so I want you to keep this page handy on the side once you've made your summary, because this is going to help you to look for those things in your drawing. So before anyone starts to answer the questions, I like to draw in as much information as I know, which means that you will need highlighters and colors and all sorts. Okay, so I've got all my colors together. And what you're going to do, so over here, you can see this is the smaller version of this. This is the question. They give you that information and then they answer, or they ask questions here at the bottom. So I always read through this at the top and I make notes on my drawing if anything is important. Okay. So what they say here is in the diagram, O is the center. Okay. So if I know that O is the center, that means there's a whole lot of theorems here which will be applicable, okay? I've got this one, angled center, 2 times angled circumference. I've got this one here that includes the center. I've got, okay, this is only 2, but then you've got all these other little things that you can use, like radii and radius perpendicular to tangent. So the fact that they've told us that that is the center, great, I already know a few things. I know that if this is my center, this to this is a radius, right? It's from center to the circumference. From here to here is a radius. So I know that those two lines are equal because radii. Okay, there's already a piece of information I've got in there, just by knowing that that's the center. Okay, KM and LM, so that's this one, KM and LM are tangents to the circle at K and L respectively. Now, when you look at that, do you not notice that it looks like the hat, right? It looks like this one over here. Okay, so it's the hat, it's drawn from the same points and it touches. So therefore I know that that is equal to that because tangents drawn from same point. That is on my little summary, which I have in front of me. Tangents drawn from same point makes my life a lot easier to have that there. Okay, so that's another piece of information we got by just reading the question or reading the information. Okay, T is a point on the circumference of the circle. Okay, so they're saying that's a point on the circumference, that's fine. Then it says KT and TL are joined. So KT is joined and TL is joined. That doesn't really do much for me, but at least I know that that's true. And then it says angle O1 is 106. So this angle here is 106 degrees. Okay, so that's fairly simple. They've pointed out a whole lot of things to me. Just before I start now, before I look at any questions, I want you guys to look at the drawing and see if you spot any theorems or anything that we've learned. Okay, I already spotted now that this is a tangent and this is a radius, and that's a tangent and that's a radius. And remember, tan is, or the radius is always perpendicular to the tangent. Same thing over there. That will be perpendicular. Remember I told you it was this extra little thing at the bottom when I was saying it funny. Radius perpendicular to tangent. Okay, that's something we just accept there. Trying to spot any others. They didn't say anything about this thing being a cyclic quadrilateral, so you can't go and assume that opposite points, you know, are supplementary unless all 4 points were on the circumference, which it is not. So you cannot just assume that that is a cyclic quad. I've seen people do that before. They go and say that the opposite angles are supplementary, but how do you know that? You don't know it's a cyclic quad or not. Okay, so question 1.1, they say here, calculate with reasons the size of T1. Okay, so I'm going to color in the ones that they want because it'll make my life easier. they want T1. Okay, so I want to know, do you see anything there? Now, the reason I mentioned the cyclic quad thing is because you may be tempted to say those two add up to 180, but they don't because it's not a cyclic quad. But I do see this thing. Watch this. This is drawn to the center, right? And it's drawn to the circumference. So what do you know about angle at the center and angle at the circumference? Angle at center is 2 times the angle at circumference. Now I know you guys might feel more comfortable seeing it look like this. Okay, where you know that one is double the size of that one. Now this looks funny, but remember the same is true for the reverse. So if I have this, okay, it's 2 lines drawn to the end. This angle is going to be 2 times that angle. So remember I showed you in that video that time that you have to match up the correct ones. This one and this one, okay, go together, and then this reflex angle and this one over here goes together. So this reflex will be double the size of that one. So it's the same thing here. This O2 is double the size of T1. But do we know what O2 is? We don't, but we do have that this angle is 106. And remember, all the way around is a full revolution. How much is a full revolution? A full revolution is 360. I just realized I forgot my calculator. I'll just get it quickly. Okay, so we know that O2 is 360 minus 106. 360 minus 106. And the reason is revolution is 360 degrees. Okay, so O2 is going to be 360 minus 106, which is 254 degrees. Okay, so as you learn things, write them in because they could help you. 254. But remember, they asked about T1. This is just, I'm going through the process here. But you know that O2 is double the size of T1 because angle at center is double the size of angle at circumference. So T1 must be half the size of that one. It must be 254 divided by 2. And the reason is because angle at center equals 2 angle at circumference. Okay, are you guys seeing how I am doing this? So 254 divided by 2 is going to be 127 degrees. Okay, so remember, everything you do, you must put your reason. So now T1 is 127. Okay, now 1.2. 1.2 says, prove that quadrilateral OKML is a cyclic quadrilateral. Okay, so I'm going to highlight it just to make our lives easier. So this is what they are wanting you to prove is a cyclic quadrilateral. Now remember, there are multiple ways to go about proving that something is a cyclic quad. Here is our special page. You can do that opposite angles are supplementary, or you can do that an exterior angle equals the interior opposite, or you can do the bow tie thing. Okay, now I definitely don't see any bow tie things going on with this pink one, but I think you could use one of these two. Okay, now remember before I started, I filled in my information, right? I showed that this was 90 degrees. Do you see how wonderfully that helps us? So you know, this is 90 degrees, and obviously that's 90 degrees as well. This is 90 and this is 90 degrees, okay? So you could say that this angle K plus this angle L, I mean, if you're looking at it over there, if we add 90 and 90, we get 180. So this K and this L are supplementary, therefore this whole thing is supplementary. Okay, so either you can use this external and that internal opposite and say because they are equal, it is a cyclic quad. I'm just going to go with the opposite angle. So I'm just going to say angle K. If If you want to, you can label it. So you can say this is K1 and K2, and that's L1 and L2, just to make it easier. So angle K1 is equal to 90 degrees Y, because radius is perpendicular to tangent. Okay. Then again, you're going to say L1 equals 90 because of the same reason. Just write it out twice. Radius perpendicular to tangent. Therefore, you can say angle K1 plus angle L1 equals 180 degrees. Therefore, what did they say? OKML, just going to label it the same. OKML is a cyclic quad, right? Because opposite angles are supplementary. And don't forget, supplementary means they add up to 180 degrees. Okay, I might run out of space here, so let me just get another page. So we're ready to go. All right, 1.3 says, we just did that. What am I missing? Oh, okay, so 1.3, prove that OKML is a kite. Okay, for something to be a kite, remember a kite looks like this. A kite looks like that, where the adjacent sides are equal. So if I can take this, again, this pink one, KMLO, and I can prove that these adjacent sides are equal, then I've proven that it's a kite. Now, again, don't you see how our preparation before this question, as in writing in the little things that we can see, helped me? Because now I can see that KO equals OL because they're radar, and I see that KM equals LM because of that. Those two tangents, remember, if they come from the same point and it looks like a hat, then they are equal. So therefore, if I just go and say both of those facts, I can say that it's a kite because the adjacent sides are equal. By the way, I mean, talking about kites and things, those are all things from grade 9 that you must learn. You must make sure you know all your different properties of shapes. It will definitely help you as well. Okay, so I'm going to go right ahead and I'm going to say KO is equal to OL because radar. Remember radar. All right, then I'm going to say KM is equal to LM. Now, just to remind yourself, that theorem, I wrote our reason here, tangents from same point. Do you see how useful this page is? Tangents from same point. Okay, so I can say therefore OKML is a kite. Why? Because adjacent sides are equal. You can write that out in full, it would probably be better. All right, so that was 1.3. Then 1.4. 1.4 says, calculate with reasons the size of angle M. So they are looking for this one over here. Okay, they're looking for angle M. Now, don't forget, we've just done, in 1.2, we've just proven that this is a cyclic quad. If these two angles are opposite and they make 180, then also these two must be opposite and make 180 because it's a cyclic quad and opposite angles are supplementary. Okay, so therefore, angle M will be equal to 180 minus this angle O1, which is 106, because opposite angles are supplementary. Or you can say opposite angles, maybe just write in a cyclic quad. Okay, so 180 minus 106 is going to be 74. So angle M equals 74. Okay, so this is your answer if you want to write it down as 1.1 to 1.4. Right, I hope that makes sense. Let's go on to example 2. All right. Okay, so example 2, let me get the questions for you guys. And I'm going to, as I always start, I'm going to read the information they've given me. Then I'm going to analyze the drawing, see if I can find anything, if I can highlight anything, and then only I'll answer the questions. Okay, in the diagram below, PT is a diameter. Okay, so we know this is the center, right? If it's the center, right, what do I know about OP, OS, and OT? They are all radii. Therefore, these 3 lines are equal to each other. Okay, then on that same note of PT being a diameter, whenever you hear PT is a diameter, I want you to remember angles in a semicircle. I can actually, if you want to go and add it to your summary, I'm just going to put it in a random little block here. You can make your summary nice and neat. So if this is your diameter and it makes an angle, remember it will always subtend a 90-degree angle, and the reason is angles in a semicircle. Okay, so go add that to your summary, please. Okay, so now that you know that this is a diameter, you immediately should know that this whole angle M will be 90 degrees because a diameter will subtend a 90-degree angle. Okay, so that's all the information we got purely from seeing that O is the center, and from seeing that PT is the diameter. Then they say it's with the circle with center O. M and S are points on the circle on either side of PT, so that's on the circumference, that's fine. And then it says MP, MT, MS, and OS are drawn. That's fine. That's all the lines. And they say M2 is 37 degrees, which we've got there. Okay, now remember, before we start, I want you to look for theorems that you know. Keep your little page on the side so you can look through them and see if you see any of those theorems. Okay, I spot this one immediately, this angle at center, because it's quite obviously drawn. So before you start, go and color that in. You know that this angle here is going to be 2 times the size of that angle there, because angle center, angle circumference. Okay, trying to see, I also see a little bow tie here. You guys see the bow tie? Although, is it bow tie? You see, remember I said to you guys, you must be careful about all 4 of the corners must land on the circumference, otherwise you might confuse yourself. This over here, I'll draw it for you, may look like a bow tie, but it isn't, okay? This is actually the exact same thing as this one. Angle at center is 2 times angle at circumference. So this one over here is 2 times that one over there, because angle at center is 2. This point falls on the center, not the circumference. I think in the videos that I made on the theorems, with this particular theorem, there was 3 different drawings, and you'll find this, the way this looks in that drawing. And I think I did tell you to be careful of that. So here is an example from an exam question where you can see this happens. Okay, so there's another one of those theorems. I don't see anything right now, but we can always check again in a little bit. So let's go to the questions, and then we'll see if there's anything we're missing. Okay, it says calculate, here's the question, calculate with reason the size of M1. Okay, so they want this M1 here. So let's reverse back. We know that this is 37. I colored over it a little bit. It's 37, this angle here, and they want this angle. Now remember, from drawing in our information, we saw that this whole thing is 90 degrees. So therefore, M1 must be 90 minus 37. Okay, so I'm going to say angle M1 is equal to 90 minus 37 degrees. And how did we know this was 90? Because diameter subtends that 90-degree angle. The reason we use is angles in a semicircle. The more you work with the stuff, guys, the more familiar it will be. It'll be easier to remember the reasons, but the key is to practice as much as you can. Okay, so 90 minus 37 is going to be 53 degrees. Okay, hope that makes sense. So this was 2.1. Here is 2.2. Okay, 2.2 says calculate with reasons the size of O1. So now they want O1. Now remember, you've just done M1. M1 is 53. Okay, so O1 is going to be double the size of M1. Are you with me? Because these two correspond. They are angle at center is 2 times angle at circumference. So we're going to say angle O1 is equal to 53 multiplied by 2. And your reason is angle at center equals 2 angle at circumference. Okay, are you with me? So angle O1 is going to be 106 degrees. Okay, and that's the only thing that they asked us about this one. This is quite a simple one. But yeah, you'll see that some of them are not too simple. Okay, let's see what's next.